So as humans today, we completely rely on electronic devices to power our modern civilization. And these electronic devices have become completely disposable. We don't design for things to last longer than their initial purpose. And so there's no circularity and there's no longevity in our electronics today. And this makes the disposal of these electronics and e-waste a huge problem. And so we thought, what if we can grow electronics like computers with nature? With nature like slime mold. And so slime mold is a single-celled organism found all over the earth. It can be found in places like leaves and trees and soil. Here at Boss Lab, we're using slime mold to grow new electronic devices. Our slime mold breadboard allows for rapid prototyping with modular components. The circuits can be designed the exact same way as traditional electronic components, only instead of being soldered together, which makes the components extremely difficult to break down and recycle, our slime mold boards are grown together. After prototyping is complete, custom compact slime mold boards can be designed and integrated into larger products following the same system that we use today. When you're done with your electronic device, open up the slime mold, throw it into your compost bin where it can decompose the food scraps in your home.
Slime mold, or the Latin name Fusarium polycephalum, is a decomposer. It's really important to the planet. Cool thing about Fusarium is it's conductive. What we did was we put it into environmental conditions in which it was advantageous for it to increase its conductivity and use that as our basis for printing into our new circuit boards. The slime mold is grown in a protected environment that can be conveniently integrated into conventional circuitry. Because these plasmonium wires allow for solderless circuit boards, we can make recycling of these components much more simpler. This means we wouldn't need to purchase disposable electronics, but instead we would grow our own electronics. These electronics would both live and die.
So how are we doing this? Well, we started with Adamatsky's research on slime mold wires. He discovered that he can get slime mold to grow between two blobs of oat agar, and that he could measure the conductivity between them. So first we tried to reproduce that experiment. That took us about a week. We then measured the slime mold conductivity, and to do that, we're doing what electronics engineers call an electrical characteristic or current voltage characteristic curve. We increase voltage across the slime mold wire, and we measure how much current is passing through the wire at any given voltage. Because the slime mold wires take so long to grow, we decided that we would try to 3D print a slime mold wire. So we actually extruded a slime mold wire through a syringe, and that only took 5 seconds. So much simpler than having to wait a week. We repeated the experiment and showed that the wire was conductive, just like our original slime mold wire. I would say roughly within a factor of 2 or 4. We feel that our particular angle of bioprinting a living slime mold will give us a special advantage in this.
None of it really matters unless we can scale this system, right? Because what we're looking to do is replace components of a natural system. And slime mold is able to work functionally with the same electronic systems that we currently have by replacing a wire. It's almost like a drop-in replacement. So the real big difference between a traditional circuit board and our slime boards is that ours are not soldered, so it can be reused, recycled, and reassembled. It's kind of like a modular system. And this is why slime mold is so amazing, because its versatility and ubiquity make it the perfect go-to.
This early evidence shows a multitude of future possibilities. Self-repairing wires, which have shown to have electric conductivity, and so slime mold will make electric devices sustainable and affordable. Slime mold allows for electric devices to be grown, not manufactured. The beauty of working with a biological organism like slime mold is we can take advantage of those properties. Once extruded, the slime mold can self-organize, and in the context of a circuit, if the wire breaks, it can also self-repair. So slime mold has long since been studied and researched for its conductivity. But to reach its full potential, there's been a missing piece. Slow growth from a single origin has kept this tech from reaching its true stride. By combining our bioprinting expertise, we've realized how to make this tech scalable, and easily mass-produced so that it becomes the sustainable, conductive technology of the future.
So where are we at today? We've successfully grown slime mold wires, and we've been able to measure the electrical conductivity of those wires. And in that process, we've discovered that there are some challenges. We're working with a living organism. Some of those challenges are its lifespan, its life stage cycle. Others are how to improve the conductivity of the slime mold wires. And we've developed some experiments to try to address that. So how can we increase the electrical conductivity of the wires? We can perhaps grow them on salt agar, which has been shown that they'll actually take up that salt. That should increase the conductivity. We also are going to feed them graphene or graphite, another substance that should increase their conductivity. So these are some of the ways that we're going to try to address these challenges. In 5 years, we will be bioprinting slime mold circuit boards that will be sustainable and scalable, making the next generation of electronic devices.
Right now, we're early in our process, and from here, we will begin to educate and spread this sticky idea. We have already filed for a provisional patent in hopes of creating a modular, solderless future. Thank you to Google and the Biodesign Challenge, as well as Boss Lab and Dassault Systems.